Hello guys, this is John Hashmat and this is a video for A2 Physics for the CAIE examinations. In this video we'll be talking about electromagnetic induction and the types of questions that you may encounter about electromagnetic induction in the final exam. In the last videos we talked about magnetic fields and the forces on a wire carrying current inside a magnetic field, and we talked about something called Flux Density, which was called B and had the unit Tesla. The flux density was defined as the force on a wire of unit length carrying a current of 1 ampere placed at right angles to a magnetic flux. But it had a simpler definition, and it was the number of flux lines per unit area. So the flux density is the number of lines in a 1 meter squared area. But what if you need to know the total number of lines in a certain area other than 1 meter squared? For example, if you have a coil here which has one turn and its area is 0.02 meters squared, and you need to know how many lines are there. If you have the flux density, for example here the flux density can be 0.5 Tesla, which is very strong. The way you can calculate the total number of lines if you have the flux density is you just multiply the flux density, which is number per unit area, by the area of the coil. And this is called the flux linkage or the flux. So the flux linkage can be calculated using the product of the flux density by the area. So here the flux would be 0.5 multiplied by 0.02, and you get the answer as 0.01, and the unit of the flux linkage or the flux is Weber, abbreviated WB. So what then if you have a coil which is placed instead of this one turn coil, and it has, for example, 10 turns. If this coil has 10 turns, we call this N. So the way you can calculate the total flux linkage of a coil is multiplying the number of turns by the flux linkage of one turn of coil. So basically you would have NBA. That's how you calculate the flux linkage of a coil of N turns. So N is the number of turns of the coil, B is the flux linkage or the flux density at that part of the magnetic field, and A is the area or cross-sectional area of one turn of the coil. So here you would have, if the flux density, for example, is 0.01, you would get the flux linkage as N, the number of turns, 10, by the flux density, which is 0.01, by the area of the coil, which is 0.02. So 10 multiplied by 0.01 is 0.1, and you get 0.002 Weber. That's how you calculate the flux linkage or the number of lines in a certain area or in a certain coil, the number of lines that are passing through a coil. Now let's move on to inducing EMF or current inside a magnetic field due to motion of a conductor. In the past videos, we talked about a charge moving in a magnetic field experiencing a force, and the force was equal to dqv. That's a force on a charge. Here you have an electron moving through a magnetic field which is pointing into the page, and it's moving upwards. So if the electron is moving upwards, then the current is downwards. If you use the Fleming's left-hand rule, as shown on the left here, the current is downwards and the magnetic field is into the page. So this electron would experience a force to the right. So this is the magnetic field and this is the force. So if this electron moves to the right, you would have an electric current to the left, in addition to the current due to the motion of the electron. So now you have two currents. And this current, this new current, is what we call the induced current. And this is due to the motion inside the magnetic field and the electron moving to the right, so the induced current is to the left, opposite to the motion of the electron. But what if you don't have an electron? You have a conductor, a complete conducting wire, and you move this wire inside the magnetic field. Then you will have most of the free electrons moving to this side, making it negatively charged, which will leave the other side positively charged. So now if you connect a voltmeter across this wire, you will get a voltage, which is called the induced EMF. So that's how you induce a current or a voltage or EMF across a conductor. You can move it inside a magnetic field. So now, whenever you move a conductor inside the magnetic field, you would experience a force on the electrons inside the conductor, which induces an EMF. If this conductor is connected to a circuit, for example here, if you connect this to a lamp or something, you'll find that the lamp lights dimly due to the current flowing through the lamp. So if the electrons are moving clockwise, then the current is moving anti-clockwise, and this is called electromagnetic induction. So moving a conductor inside the magnetic field creates an induced current due to an induced voltage, negative and positive charges. So now what can we do to increase the EMF or increase the current? To increase the EMF, we need to increase the number of positive and negative charges across the ends of the conductor. To increase the number of negative charges and positive charges, you need to overcome the electrostatic repulsion, which means you need a greater force. If you need a greater force, in this case, you need to increase the speed of the motion, or the speed of the moving electrons inside the magnetic field. So you need to move faster. Another thing that you can do to increase the force on the electrons is by increasing the flux density of the magnetic field. So you would use a stronger magnet or stronger magnetic field, which gives you a higher value for flux density. So that's how you increase the force. That's how you accumulate more charges. So basically, if you need to increase the EMF, you need to go faster, move the conductor faster. That's increase the rate of movement, or increase the number of lines. So basically, the EMF should be proportional to the number of lines being cut, which is the flux density, or inversely proportional to the time during which you cut them. Also, it should be proportional to the flux linkage, which is proportional to the number of turns if you have a coil, or the flux density, or the area. So basically, you can say that the flux linkage is proportional to, the EMF is proportional to the flux linkage, or the change in flux linkage, and inversely proportional to the time. That's called Faraday's law. So how can we use Faraday's law? Faraday's law states that the induced EMF is equal to the rate of change of flux linkage. So an example would be if you have a coil which has an area 0.02 meters squared and has 10 turns and moves at a speed of, for example, let's keep it simple, 1 meter per second, from a region where the flux density is 0.5 Tesla to a region of 0.3 Tesla. So the way that you can calculate the induced EMF in this coil due to this motion is the change in flux, which is change in NBA over the change in time. So how can you get the change in flux? Notice that the number of turns did not change, the cross-sectional area did not change, only the flux density changed. So we write this equation as N, same, 10 multiplied by 0.5 minus 0.3, that's the change in flux density, multiplied by the area, which is 0.2, divided by, how can you get the time now? You have a motion which has a certain speed. All you need now is the distance. So what if the distance between this region and that region is 0.1 meters, 0.10 meters, that's 10 centimeters. So the way you calculate the change in time is dividing the distance by speed, which would give you 0.1 over 1, so you get the time as 0.1. And of course you get the answer in volts. It's an EMF. So that's how you use Faraday's law. Now, what happens instead if you did not move the coil, you rotated the coil? If you rotate this coil, if you have this magnetic pole here and the field is going like this, if you have a coil here, and this coil is rotated, so it becomes horizontal, but in the same region. What happens then? If you rotate this coil from a vertical orientation to a horizontal orientation, now you would have no linkage whatsoever when the field is parallel to the area of the coil. No cutting, or the field lines do not pass perpendicular to the cross-sectional area of the coil, so no flux linkage. So here, at first, for example, we'll use the same values. B 0.5, area is 0.2, and the time of rotation is 0.1 seconds. So, and the number of turns, by the way, is still 10. The way you calculate the change in flux linkage is by changing the area. Basically, you didn't change any other aspect. The number of turns stays the same, the flux density in this region stays the same, and you have the time in which you created that change. So now you have 10 multiplied by 0.5, which is still the same region, but now you change the area from 0.02 perpendicular to the flux to 0. Then you divide by the time. What happens then if you rotate this coil a further 90 degrees? Now the area is in the opposite direction, or pointing in the opposite direction. So the EMF would be 10 by 0.5 multiplied by 0.02 minus negative 0.02. If you do this in the same time, then you divide by 0.1. You'll find that this induced EMF is much greater than that induced EMF. So that's how you use Faraday's law. You calculate the change in flux, then you divide it by time taken to change the flux linkage. Okay? This is called Faraday's law. So the induced EMF is equal to the change of flux linkage divided by time, or the rate of change of flux linkage. Now, let's see the effect of this current on the motion. We said that for the above example, the induced current in a conductor moving upwards in a magnetic field pointing into the page is to the left. If you use Fleming's left-hand rule now, you will find that if there is a magnetic field pointing into the page and there is a current to the left, there will be a force downwards. So you have a force, this is a magnetic field into the page, and the induced current is to the left. So this means while moving the wire upwards, the wire will experience a downward force opposite to the motion. This is called Lenz Law. So what does Lenz Law state is that the induced current or EMF opposes the change in flux linkage. So basically, if you try to move the wire upwards and there is an induced current, this induced current will create an opposite force to the motion. If you try to move it to the right, you will experience force to the left. If you try to move it to the left, you will experience a force to the right. So basically, this can lead us to get a new perspective or new method of how to determine the direction of the current. If you see the pictures on the left here, you have both hands using Fleming's hand rule with the same fingers. Here there are similarities here. Same pointing of the force or motion. Same direction of magnetic field, but the current is reversed. So basically, if you have a current in a certain direction, you will have a force in a certain direction which is perpendicular to the current. But if you reverse the current, you will get the opposite force, or motion in a certain direction will give you a force in the opposite direction. So instead of using Fleming's left-hand rule, you'll use the same orientation of your fingers on your right hand. So if you use the right-hand rule here, and there is motion upwards and the magnetic field pointing into the page, the induced current will be to the left. So that's how you use the right-hand rule to figure out the direction of the induced current in a straight wire cutting a magnetic field or experiencing a change in flux inside a magnetic field. So this gives us a new representation for Lenz law and Faraday's law together. So the induced EMF will be equal to the rate of change of flux linkage, d phi by dt, but with a negative sign. This represents that the induced EMF is opposing the change in flux linkage. So this is a combination of Faraday's law and Lenz law. Okay, let's move on. Now, if you try to think about Lenz law, that any motion is opposed by the induced current, or any change in flux is opposed by the induced current. If you have a magnet here moving to the right towards a coil of wire, there is a magnetic field, and the number of lines in linkage with the coil at this distance is, for example, one line now, but as you move closer, the number of lines linking with the coil increases. So there is a change in flux linkage. For example, if you have a north pole pointing towards the coil, and you get this north pole closer and closer, you'll find that the number of lines in linkage with the coil increases. So there is a change in flux. This causes the coil to have a current flowing through it. So there is an induced current, and this induced current wants to oppose this motion. So what it does is it flows in a certain direction that creates a north magnetic pole on this side, so there will be a repulsion between the magnet and the coil. So the more you try to push this magnet towards the coil, the more repulsion you will get. So that's how Lenz law is applied in this situation. What happens if you try to remove the north pole away from the coil? There will be an induced current, since the number of lines will be decreasing in linkage with the coil, so there will be an induced current in the opposite direction, creating here a south pole, which will also try to stop the motion. Since you're moving away, the south pole would attract the north pole, creating a force opposite to the motion. So motion to the left, there will be a force to the right. If you try to get a south pole near the coil, the induced current will be so that there will be a south pole here repelling the magnet. If you try to move the magnet away with the south pole, you will create the opposite current, creating here a north pole. So it will be attracting the magnet instead of repelling it. That's also opposing the motion. There are some applications for Lenz law, or uses for Lenz law. Basically, if you place a rotating disc made of metal, for example, or steel or aluminum, and this rotating disc is inside a magnetic field. For example, there is a north pole here, there is a south pole here, so there's a magnetic field in linkage with the disc, but the disc is rotating. So basically, this area here is moving very fast. This is moving with lower speed, this is moving with lower speed, and so on. So different parts of this disk are moving with different speeds and have different rates of flux linkage. So here you have phi 1, delta phi 1, here you have delta phi 2, here you have delta phi 3. So there will be a difference between parts having different EMFs, which means there is a potential difference between parts inside this disk, which leads to currents. So you have different EMFs induced. This creates a potential difference, and this potential difference causes currents. These currents are called eddy currents. And they're called eddy because they're just spiral currents. The electrons keep rotating in circles, which means that these currents are not useful, but they cause a heating effect, which means that the energy of rotation of this disk keeps decreasing because it keeps converting to heat energy. So you lose energy as heat. This causes loss in kinetic energy. So basically, if you want to stop this disk from rotating, you just place it inside a magnetic field. It keeps cutting the field, and there's an induced EMF in each part of this disk, and there's a potential difference between parts of the disk. So that will create an eddy current in each section of the disk, and these currents heat the disk up, making it lose kinetic energy since this heat is dissipated to the surroundings and increases the internal energy of the disk, so the kinetic energy must decrease. So that's how you stop a moving metal object. Just make it move inside a magnetic field that will create eddy currents, and eddy currents will generate heat, reducing the kinetic energy of the motion. There are some theories now to use magnetic fields and electromagnetic induction to achieve levitation. Even some car companies are experimenting, with magnetic levitation, but it doesn't make that much efficiency because of that much heating effect caused by the magnetic field cutting and creating eddy currents. So basically, if you have a coil here which has an alternating current source, so the current keeps going clockwise, then anti-clockwise, creating a changing flux. Around the coil, and here you have an iron core that increases the flux density. If you try to place a piece of ring or an aluminum ring on top of this coil, what you will experience is this changing flux will induce EMFs with different magnitudes in this ring, so you will have eddy currents. And this current will oppose the change in flux. So if you have at a certain time a north pole here, you will induce a north pole here. This will cause repulsion, and you will find that this ring will just shoot up out of the rod, and this is due to the repulsion between the two magnetic fields. So you have a current here. If it's anti-clockwise, you will have this current going like this, creating a north pole at the bottom and the south pole at the top. So the repulsion between the two north poles is greater than the attraction between the north pole and the south pole. This will cause a resultant force of repulsion, so the ring will just get out of the rod. If the mass of the ring, however, is too heavy, then the ring will just float at this distance above the coil. So this is called levitation. If you increase the frequency of the AC, you will increase the change or the rate of change of flux linkage. So this will create a stronger force. Then the force it shoots up out of the rod will be greater, or it will just hover at a higher distance where the flux density is a little bit less. So these are the applications of inducing EMF in a coil or using a changing flux to induce an EMF. Okay. Now let's see what happens if you bring two coils next to each other, one carrying an alternating current, so there is a changing magnetic field, or a changing flux. This will induce an EMF in this coil, and you will find that if this coil is connected to a lamp, the lamp keeps switching on and off according to the frequency of the AC. This is because a changing current has a changing flux. And this flux induces an EMF in the second coil. So there is an induced current in the coil. So what happens if the current in the first coil is a sinusoidal current? So this is the current in the first coil. So we'll call this coil 1, we'll call this coil 2. So this is a current in coil 1. You'll find that the created flux here follows the same pattern. As the magnitude of the current increases, the flux around coil 1 increases. As it decreases, the flux decreases, and so on. So it creates the same type of flux, same pattern as the current. What will be the induced EMF like in this coil? You'll find that if you use Faraday's law and Lenz law, as mentioned before, E is equal to negative d phi by dt, then the EMF induced in coil 2 will be equal to the differentiation of the flux with respect to time. The differentiation of a sine function is a cosine function. But you have a negative sign here, so you will find that it will be a negative cosine curve. So that's how you induce an EMF with two coils. This is called mutual induction. So you have a changing current in the first coil, which creates a changing flux. So this change in flux linkage with the second coil induces an EMF. This EMF is equal to the rate of change of flux linkage, and it has a negative sign, which means that it is opposing the change in flux, but the alternating current keeps going, so there's an induced current here that keeps going. So what if you have a direct current that reverses direction over a short time? For example, if the current in the first coil varies like this, you have a constant magnitude in a certain direction, then at a certain point the current starts changing magnitude and changing direction until it reaches a constant magnitude. The flux will vary in the same manner. So constant magnitude of flux, then changes, then constant. So this is how the flux and the current vary with respect to time. This induces an EMF which varies like this. So using E is negative d phi by dt, you will get the gradient of these graphs. So here at this part, the gradient is equal to 0. So the EMF will remain 0 on the x-axis. So this is the induced EMF in the secondary coil. During this region, there is a negative gradient with a steep value, which means you have a sharp change in flux linkage, which means that you will induce a large EMF, but since the gradient is negative and the EMF is negative d phi by dt, you will have a high positive EMF. And this keeps going as long as the rate of change is constant. Then it drops back to 0 since the gradient of this graph is 0. So it remains on the x-axis here. So this is how you use Lenz Law and Faraday's Law to plot a graph or sketch a graph of how the induced EMF in a secondary coil compared with a primary coil carrying a varying current which creates a change in flux linkage with another coil. The last thing we're going to talk about is a common question in the past papers, which is the difference between the voltage induced in a hole probe and the voltage induced in a coil when you place it near another coil which is carrying a current either constant or varying. So for this example, I'm using a coil with a direct current which I can control. For example, I can place a switch here and I can switch on the current, then I can switch it off. So this is how the current varies in the coil, and this here is a hole probe, and there is a voltage induced in the hole probe. You will find that when there is no current, there is no reading on the voltmeter of a hole probe, or there is no reading on a hole probe, and once there is a current, there will be an induced voltage here. Basically, that's because the hole probe just measures the flux density of the field. Once you have no current, there is no flux, so no voltage in the hole probe. And once you have a high current, there will be a voltage because there is a flux density here. And when you turn off the current, it goes back to zero. Same as the current. But a coil placed near this design will have a different result. So during this region, when there is no current, there will be no EMF. Basically, because there is no flux at all, so no change in flux. But during the change in flux from no current to high current, or from no flux to high flux, there will be an induced EMF, a very sharp and steep induced EMF. But after that, there is a constant field. So a constant field will not have a change in flux, so there will be no induced EMF during the time where there is no change in flux. When you switch off the current, you create an opposite change in flux. First it was an increase in flux, now it's a decrease in flux, so you will have an opposite induced EMF. So this is the difference between the two magnetic fields or the two induced EMFs, one from a hole probe and one from a coil placed near a magnetic field. Now let's go over what is discussed in electromagnetic induction. First, we mentioned something called the flux linkage, or the flux, which represents the total number of lines in linkage with a certain area of a conductor. And this flux linkage is calculated using the equation phi is equal to BA, where B is a flux density, number of lines per unit area. Then you multiply by the area to get the total flux. If you have a coil with n turns, then you multiply by the number of turns to get the total flux of the coil. And we said that if you move a conductor inside a magnetic field, it will experience a force on its free electrons, creating a potential difference across its ends, causing a negative and positive charges, so creating an EMF on the wire or the conductor. And this flux is proportional to the rate of change, and this EMF is proportional to the rate of change of flux. So the faster you move, the higher EMF you get, the stronger the magnetic field, the higher EMF you get. And this is called Faraday's law. So Faraday's law stated that the induced EMF is equal to the rate of change of flux linkage. And you calculate that by calculating the change in flux, the change in NBA, number of turns, flux density multiplied by area, over the change in time. So this can be done by rotating the coil, or moving the coil away from the magnet, moving the coil towards the magnet, or any kind of relative motion between the magnetic field and the coil that will cause a change in flux linkage, and you calculate it by change in NBA over time. We mentioned Lenz Law, which states that the induced EMF or the current opposes the motion. That gave us the right-hand rule to predict the direction of the current. So the thumb points towards the motion of a conductor, the first finger points toward the magnetic field, and the middle finger gives you the induced current. And that led us to a new equation, or a new version of Faraday's law. Added here is a negative sign which represents Lenz law that the induced EMF opposes the change in flux linkage. And we've seen that how that works with coils and magnetic fields. So whenever you move a magnet towards a coil of wire, a magnetic pole will be created on that side of the coil that repels the magnet. Whenever you try to move the magnet away from the coil, a magnetic pole will be created that attracts the magnet to stop it from moving and stop the flux linkage change. We also saw how Lenz law can be used in certain applications. Here you have a rotating disk which has different rates of flux linkage change with a magnetic field. So you have different EMFs induced in different parts of the disk, which creates eddy currents. And these eddy currents have a heating effect, which causes the kinetic energy of the disk to decrease, and that's how it can stop a very fast rotating disk immediately, almost immediately. So basically the disk gets very hot and loses much of its kinetic energy and stops. Also, Lenz law can be used for magnetic levitation. If you have a coil carrying an alternating current, so you have a changing flux, which creates a change in flux linkage with a metal disc or a metal ring or any metal object. So eddy currents will be created with magnetic poles opposing the magnetic pole of the coil. For example, here now you have a north pole. In another instant, you will have a south pole. A south pole will be created under the disk, and there will always be repulsion between the disk and the coil, or the ring and the coil. So there will be a force upward on the disk, which opposes the weight of the disk. If the weight and the upward force are equal, then the ring keeps floating. If the upward force is greater, this ring will shoot out of the rod until it's outside the range of the magnetic field of the coil. We also mentioned how two coils, one carrying an alternating current and one just connected to a closed circuit, can have mutual induction. So basically the AC in the first coil creates a changing flux, which causes a change in flux linkage with the secondary coil and induces an EMF in the secondary coil. If the AC is a sine function, you will find that the change in flux will also be a sine function, which causes an induced EMF with a phase difference. So it is the gradient of this graph. That's why there is a phase difference. So if you're asked why is there always a phase difference between the induced EMF and the AC in the primary coil or the first coil, that's because that the rate of change of flux linkage is what causes the EMF, not just the change. It is the rate of change. That's what causes the phase difference between the two EMFs or the two currents. So whenever you draw an induced EMF, you always take the gradient of the change in flux and reverse the sign of the gradient. For example, like we used here, so the gradient was 0, we draw 0. Here the gradient was negative, so we get a positive EMF. And when it goes back to 0, you draw the EMF induced as 0. So this concludes this video about electromagnetic induction. I hope it was useful, and I will see you in the next video.